In this video, I'm going to show you how you can add any op-amp you want to into your LTSpice simulation. So firstly, I'll show you why this is important. If I create a new schematic in LTSpice and I go to my parts list, there is a whole category for op-amps. And if we go into there, there is a bunch of options available, but there's also a bunch missing. So for example, if I look at the common LM family, there's only two options here. Things like the really common LM741 aren't included in LTSpice's default components. So what can I do? Well, firstly, I can look up the part. So if I look up LM741, and it's usually helpful to add that SPICE model to your search, then for TI components, particularly, you'll find a page that looks like this with the datasheet, product information, and support. Other manufacturers will have a similar thing. Click on that one, and then in the case of TI, it's under the Design and Development tab, so you can just scroll down or click on that, and you'll find this PSpice model. Download that, and it'll come through as a zip folder, and then you can move it to wherever you like. I've moved it over into my 2300 folder. So then you just want to extract that. And this is the directory that you need. So these are all of the files that relate to your LM741. The important one for LTSpice is this .lib file. So we want to get the directory to that one. So I might just copy the path from up here actually. So I've just copied that full complete path. Now I'm going to go over into LTSpice and see this .t button up here that says Spice Directive. When we click on that, we can add different commands. So in this case, what we want to do is we want to include a library. And all we need to do is type .include, paste in that directory, and just add onto the end the file that we want, which was the lm741.lib file. Press OK on that and just click it somewhere into your schematic. So then from there, we want to actually add in the op-amp. So again, we'll go back into our parts menu and that op-amp category. And the one that we're looking for is called op-amp 2. So this one is a basic operational amplifier for use for subcircuits in the file ./lib blah, 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 blah. So that's the format we've got. We've got a .lib file. Place that down. And now we just need to take one more step to actually make this an LM741. And that's to find out what the subcircuit is called in that .lib file. So go back to our directory, and if we open up this one here just in a notepad or something like that, then you'll see this .subcircuit and a name following it. In this case, that name is just LM741, so it's exactly what the component's called, but sometimes it will have sort of extra bits on the end or whatever else. So just copy that name, and what we're going to do is right-click on our op-amp and see this generic value op-amp 2 here. We just want to replace that with the actual subcircuit name. In this case, that was LM741. Press OK, and you now have an LM741 ready to go. So to test that this is all working, let's quickly build an inverting amplifier. So one thing I like to do with the power supply rails is I like to put them off to the side. It just makes it a little bit neater to work with. So I'll show you how you can set this up. So you just got to pretty much build these in with a wire up the top that goes to nowhere. And then what we'll do is we'll name those nodes. So if I call this one here VCC, and then I also paste that VCC onto the node where my positive supply is, then those two are now connected. So when I set this to 12 volts, that means that VCC is 12 volts here, and it's 12 volts over on the positive supply rail of my op-amp. Same thing I can do here. So I'll make this one -12, and I'll call it negative VCC. Click it here, click it to my negative supply rail, and that's now connected to that. So that's all powered and ready to go. Now we just got to create the actual amplifying circuit and put in our input signal. So to do a simple inverting one, we want one feedback resistor, one incoming resistor, and a voltage source. And we'll just wire those all together. And then we just need a ground on the non-inverting terminal there. So I'll call that output node VO so that we can measure it easily. I'll let this resistor just be 56K perhaps, and then we'll make our incoming one 10K. And we'll set this up to just be a sinusoidal source with a 0.1 volt peak at 1 kilohertz. So with these numbers, we should expect a gain of about 5.6. So let's test it and see if it works. We'll go 10 milliseconds, with a small time step. So it ran, so that's always good. So now what I'll do is I'll probe the output and the input so that we can compare them. And that's looking pretty good. So we can put some cursors on there to check. This one here drops down to the 100 that we set it to. And at the same time on our VVO, we're getting about 570 millivolts. So we're getting a gain of about 5.7. So that's exactly what we expected. So that is it for this video. And that's just one way that you can kind of add in a custom op amp for your simulation purposes. There are other ways that you can see online, but I like this one because you can just put the file wherever you want and just drop it into your individual simulation. So that's it for this video. Hopefully it's helpful. I'll see you later.